Hello, welcome back to my class. Today we're going to discuss about the behavior of the graph. So when it comes to behavior of the graph, we have increasing or decreasing, local extrema, which is including local maximum and local minimum. We also have concavity. We have inflection point. So these four types is going to use to describe the behavior of a graph. All right, so now let's take a look at this graph. I have a graph. So when you look at this graph, well, let's talk about which part is increasing, which part is decreasing. So when it comes to increasing, I'm going to use a blue highlight to highlight increasing part. So increasing is as S gets bigger, Y gets larger. So that means if you look at the graph from the right from the left to the right, the graph is going up. So this is increasing, like this part, right? This part is a increasing part. What other part is increasing? This part, right? This part also increasing. So here is the increasing part of the graph. What about decreasing? Well, decreasing is as S gets bigger, our Y gets slower. Or if you look at the graph from the left to the right, this part is decreasing. So at this middle section, this is a decreasing of the graph. So where's the local extrema? Local extrema is when this graph from a increasing become decreasing. That means local extrema, or from decreasing to increasing is local extrema. So I am going to use a red pen to point out what is local maximum and local minimum. Sorry. So local maximum will be what? From increasing become decreasing. So this is our local maximum. Well, this is very important. Why we call it local maximum? So when we define it, local maximum is the behavior change. When the graph behavior change, doesn't have to be maximum. Because if you look at the point in here, point B and point A, point B definitely bigger than point A, right? But our B is not a local maximum. A it is local. It's the local maximum because the definition of a local maximum is the graph changing from increasing to become decreasing. That is our local maximum. Or you can think about a local vertex, but we call it local extrema. Well, similar idea to local minimum. Where do you think it is? It's in here. So local minimum is when the graph starting from decreasing and then change to increasing. So look, the graph is going down and then going up. So this is local minimum. Now, concavity. All right, so concavity, the concave up and concave down. So now look at this graph. We have two sections is increasing. One is look like this one, right? The other part is more like this one, correct? So if you look at these two parts, they're both increasing, but the rate increase is different. Like these have a U open it towards down, whereas this one is more like open to the up on the top. So in this one, we call it concave down because pointed downside. And this is increasing, but concave up, going upwards. So similarly, if I have a decreasing graph, let's say this is decreasing, right? These also decreasing. They both decreasing. Let's say this is our y, x, y, x. So for our first graph, it's decreasing, but this one is what? They open up like a U, like the letter U. So we call it concave up. Whereas this one is more like an N, a letter N. So this one we call it concave down. They can both be increasing, but the concavity is different. Now the next part is inflection point. So inflection point is, if you remember this graph, okay, can you really fast to tell me what is this graph from our toolkit function? By now you should know that very quick. Is y equals to s to the cube, which is the cubic function. So this whole function is a increasing function. Is there any local extrema? Oh, that means local minimum or local maximum? No, right? So that means no local extrema. But what about concave? Well, it concave two-way. From the first part, this part, it concave down, right? This one is concave down because it's pointing downward. It's increasing but concave down. And then later, this part, it concaves up at the second part. So where the concavity behavior change at that point, which is in this case at the origin, so this point is inflection point. The definition of inflection point is the concavity change from concave down to concave up, or change from concave up to concave down. Either way, this is called inflection point. So example, now let's discuss about how to describe the behavior of this function. First of all, what's this function? This is a reciprocal squared function. Okay, so this function on the left side is increasing. So that means on the interval from, not including, negative infinity to 0, the function is an increasing function. And then on the other side, which is on the interval 0 to positive infinity, the function is decreasing. And we know that there's no local maximum or local minimum. So that means there's no local extrema points. And now let's take a look at the concavity. This one is increasing, this part is increasing, and open up like a U. So that means this is concave up, and this side is decreasing, also concave up because it's open up. So that means I can say, hey, on the interval, which is the whole domain, the function from negative infinity to infinity, union to another interval, 0 to infinity, the function concave up. We can have another example, such as this one. Parabola. When it comes to parabola, we have what? So first of all, increasing or decreasing? Well, from negative infinity to 0, not including 0, because at 0 you don't decrease anymore. The function decrease. And then from 0 to infinity, which is on the right side, this part, the function increase. And since the function behavior changed from increasing to decreasing, so that point is going to be our what? There is a local minimum at the point 0, 0, the origin. And the whole function from negative infinity to infinity, they are all concave up because they're all pointing up, right? Okay, so that's it for today's lessons. Let me know if you have other questions.